Okay, so today I thought we'd have a look at Chapter 3 of the Year 12 Specialist book. Last time we did functions in the Year 12 Studies book, so we looked at some exponentials and logarithmic functions. In this specialist book we explore different types of functions. Some of which are also applicable in methods, like you do use, the f of x notation, like what we're going to be looking at here, for example. So today I don't have my drawing pad with me. I didn't want to make this one too long-winded or too long because the other one was 41 minutes. So I thought that we could just have a talk through the chapter for this one and perhaps make it a little bit quicker and a bit more concise. So this is the content, obviously, of Chapter 3. And we start with composite functions. We have seen previously, so in Year 11 you would have looked at relations and functions and what they mean, and the f of x notation, which they talk about there. So it's a different way of representing y. So in previous years you would have had a function of y in terms of x. Now we're calling it f of x instead of y. So f of 3, for example, is just what is y when x is 3 in terms of a different notation. So composite functions, we go a step further, and we don't just have f of x now, but we've got f of g of x as an example. So we're plugging x into the g formula, and then we're plugging all of that into the f formula afterwards. So they've got different ways of writing the notation in the description box there, and they've got a picture underneath which basically says if you've got f of g of x, x goes into the g machine or the g function first, spits out an answer, g of x, and then that goes into the f machine and you get f of g of x. So basically, whatever is in the centermost bracket, you deal with first. So x is in the centermost bracket, and then g of x is in the going outwards where the brackets are, is the next thing that you do. So plug x into g of x, and then after that you plug all of that into the f function. And obviously if you had g of f of x, it would be the reverse. You'd have the f machine first in the blue diagram, and then you'd have the g machine following that in the red or orange diagram underneath. So in general, f of g of x, that's just another notation for it, doesn't equal g of f of x. And then you've got an example where you are basically just, it's a lot of substitution. That's basically all of this is, but it's still good practice. And then obviously if you've got, say in 3b, you've got g of f of a number, you're going to get a number output. But if you've got f of g of x, for example, you're going to get an output in terms of x for f of g of x. So state its domain and range. So those ones, you can work it out by hand, and then you can check with your calculator if you've got a graphing calculator, which I recommend. It's always a foolproof method just to see if you're on the right track. And you're also practicing your calculator skills by using your calculator. But basically anything under a square root sign always has to be 0 or above. So when you're checking for things like domain and ranges, That's a handy thing to know. Or anything on the bottom of a fraction, for example, can never be 0. So that can often result in asymptotes, and later in the chapter we're going to see some where we get that situation happening. But basically, just to run through 3a, if you've got f of g of x of, if you calculate that, you'll be putting in the g of x into the f of x formula, so you're going to get 9 minus the square root of x squared plus 4 under the square root sign. And so then you can work out the domain and range from that. And then you've got other questions that are very similar, 4 and 5, and then 6 of 7 where it gets a bit more complicated. And then we move on to inverse functions. So the operations of plus and minus, times and divide, inverse operations as one undoes what the other does. So if you've got times 2 and then divide by 2, if you do that to any number, you're going to get back to your original number. So it's a similar concept with inverse functions. So you can, and I like these boxes that they have, it makes it really clear to see what's going on. So say you plug in a number 1 to y equals 2x plus 3, you're going to get an answer of 5. Plug it into the inverse function, which is the function that follows, and it undoes what the first function does, and you're going to get 1 as the output. So you ended up with the same number that you started with, okay? But not all functions do have an inverse function. It's only restricted to some functions. And that's what we look at here in this bit. So you've got one-to-one functions and many-to-one functions. So a one-to-one function is any function where for each x there is only one value y, excuse me, and for each y there is only one value of x. So equivalently, a function is one-to-one if f of a equals f of b only when a equals b. So that basically means that, say you've got a quadratic function, and say if you input a value of x and get a value of y, say if you've got y equals x squared, and you input the value of 2, x equals 2, and you get 4. And then, so we've put the number into a function, into the x squared function as our first function. If that was to have an inverse, and if you put 4 in as the value of y into the inverse, if there wasn't such a thing as an inverse function for that quadratic, you'd get 2 solutions. You'd get plus 2 or minus 2. So we're not getting, like in the first example, we had 1 as the input, 5 as the output, and then we put it back into the inverse and got 1. So we only got 1 value back. So anything which has 2 solutions, you're not gonna always end up exactly with what you started with before. So they're not inverse functions, because in the example of a quadratic, it doesn't satisfy the horizontal line test. So basically, one-to-one functions satisfy both the vertical line test and the horizontal line test. So this means that no vertical line can meet the graph more than once, and no horizontal line can meet the graph more than once. So if the function is one-to-one, it will have an inverse function which we denote as f minus 1x. So yeah, that denotes an inverse function. So if it does have an inverse function, basically it's quite easy. To find the inverse of a function, we just swap x and y over wherever they are. So in the example, it says y equals 5x plus 2. So that becomes x equals 5y plus 2. So we're just switching f and y around. And as a result, you're going to find that the domain of the inverse is equal to the range of the original function, and the range of the inverse is equal to the domain of the original function, because it's basically the first function just with the variables switched over. So it makes sense that the domain would then become the range, and the range would then become the domain when you're finding the inverse. So you've got, yes, and they're reflections in the y equals x graph, the original function and the inverse are reflections in y equals x. So we'll have a look at some questions. A self-inverse function is symmetrical about the line y equals x, but the inverse of a self-inverse function is equal to what you had at the start, the original function. So you'll find that with a graph like y equals x, that has a self-inverse function, because if you switch x and y, if you've got y equals x, you'll switch it and get x equals y, which is the same as y equals x. So that's self-inverse, and it's the same if you've got y equals 1 over x in the second example, under the blue box. If you switch x and y for that one, you'll get x equals 1 over y, which if you rearrange it, it ends up being y equals 1 over x. So you had the inverse function is the original function, it's the same. So that is a self-inverse function as well. So yeah, so these initial questions are just asking you to graph f, its inverse, and y equals x on the same set of axes. And you should find that the inverse and the original function are reflections in the line y equals x. Yes, number 3. You should find that the domain and range of all of these functions here are the... So you should find that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. That's what you should find. That's a hint to know if you got the second part of question 3 right. If the domain turns out to be the range of the inverse, and if the range of the original function turns out to be the domain of the inverse, you know that you've it's a good test to see if you've done the question right. So interestingly, in E and F, you're going to find that when you find the inverse of those, it'll be the same graph, because if you reflect E and F in the line y equals x, it'll be the same graph that you have. So yeah, just moving through and having a look. So in number 10, where we've got the images, we look at the horizontal line test and discover that if we put a horizontal line through the first one in I, it'll always go through just once, and so that passes the test. In II, where you've got a quadratic, and triple I, where you've got a cubic, they won't satisfy the horizontal line test. So those are not one-to-one functions, and so hence they do not have an inverse function. The only way in which you can get an inverse function with a quadratic or with a cubic is to make a new function and restrict the domain. So if you had in 10bii, if you took half of the quadratic and made it a function for x was greater than or equal to 1, it would then be 1 to 1 because that function would then satisfy the horizontal line test, and so then it would have an inverse function. So we've talked about self-inverse, like in 17. So a lot of these questions are quite repetitive. So prove that e to the x and ln x are the inverses of one another. So what you need to do for that one is find f of g of x, and if that is the identity function y equals x, you're on the right track. And then find g of f of x, and if that's also the identity function x, and if all of those three things equal, you've proven that f of x is an inverse function to g of x. And so then you can use that information to find the inverse of bi and bii. So then we look at reciprocal functions. So a reciprocal of anything is 1 over what you had. So the reciprocal of 3 is a third. The reciprocal of 5 is a fifth. So a reciprocal function is the form of y equals k over x. The most simple one that we've got is y equals 1 over x, the rectangular hyperbola. So you've got a list of dot points there about the features of that graph. So you can look through that. And then we've got some graphs to, so yeah, it's a very short section there, 3C. So number 2, prove that y equals k over x is self-inverse for all KER. So that's pretty simple. You just switch x and y around, rearrange it, and you'll get y equals k over x. So that's the answer to that, really. And then in number 1, you draw some graphs and look at the transformation that you could use to map y equals f of x onto y equals g of x. So that's something that you can think about there. The reciprocals of other functions. So this is when they get a little bit more complicated. So you don't just have x on the bottom anymore, you've now got f of x on the denominator. So okay, so there's an investigation here, and it says from what you should have found from the investigation of these points. So the zeros of f of x become vertical asymptotes of 1 over f of x, which makes sense because anything approaching 0 on the bottom of a fraction, the whole fraction is going to approach infinity, whether it be in the positive direction or the negative direction, so going upwards to infinity or downwards to negative infinity, and then you'll have a vertical asymptote in between. So yeah, you can read through those. So graphing all of these ones in 3D is going to be referring back to this table if you graph it by hand, and then of course you can check it with your calculator after that just to check what you've done. Yeah, and you're using the table to figure out how to graph the reciprocal of these 3 functions in question 3 as well. So it's just going through and saying, okay, Whether these graphs have zeros, some might not have zeros, but some might. Where do they have vertical asymptotes? Where have they got local maxima or minima, and what does that imply about the reciprocal? Where are they negative and positive, and what does that imply for the reciprocal? And then obviously if you've got f of x tending towards 0 on the bottom of a fraction, 1 over something that's getting increasingly smaller is going to get increasingly bigger. And so that will tend to infinity, plus or minus. And if you've got something on the bottom of a fraction getting increasingly big, the whole fraction, 1 over a really, really big number, is going to be very small. And if you make the number on the bottom bigger, it will get closer and closer to 0. So that's that last point in the box, what that is referring to. So that's 3D. Rational functions result from the division of one polynomial by another polynomial. So to determine the equation of the horizontal asymptotes, I'm just reading out the blue boxes here. We consider the behavior of the graph of the function as the modulus of x tends to infinity. So that basically means when x is getting more and more negative, we look at that and we look at it from that angle, and also from the angle where x is getting more and more positive. So when x approaches negative infinity, and when x approaches positive infinity, is basically just what that is saying there in that box. So we look at the two aspects, and that determines the equation of the horizontal asymptote. So just having a look at this here. So in the first question of 3E, it follows this example, this worked example that they've got. So yeah, these questions are very, very repetitive. So you'll nail this chapter if you get the common theme or the common message. I mean, some of the questions get harder and they've got variations in them, or some use letters like in number 3, where you obviously can't graph it. So that one really takes the teachings and the learnings from 1 and 2. So if you nail those, and if you know how to do them by hand, you're going to know how to do number 3, because it's just going to follow on from that, but using letters. So just considering this one in the example. So you've got a rational function with a linear divided by a linear. Find the asymptotes of y equals f of x. So first of all, in A, they rearrange that function to get so that you can find the asymptotes. So obviously, just having x on the bottom of a fraction just makes it a whole lot easier than having it also up the top. So what they've done here is they've times to get rid of the x on top and just have a number. They've times the 2 by x plus 1 so that they cancel. But in order to do that, they've actually added 2 to the whole thing. So you have to minus 2 to the 6, because 2x is what you had at the start, 2x. 2 times 1 is 2, so you're adding on 2, so you have to minus 2 from the 6, and then you get minus 8. So that the x plus 1's cancel, and you just get 2, and then you have minus 8 on x plus 1. I mean, if you graphed it, you could see it on the graph where the asymptote is on the calculator, but to do it by hand, this is the way that you do it. And for all of the questions actually in the first part here. And then you look at where the bottom of the fraction is 0, so that's when x is minus 1, so that'll be an asymptote. And then you look at when x tends towards negative infinity and positive infinity, you look at that to get the horizontal asymptote. So yeah, you figure those things out. Find the intercepts when x and y are equal to 0. And then with that information, you've got enough to be able to draw the graph. Once you've got the intercepts, once you have the asymptotes, it's pretty simple then to be able to draw the graph with that information, and then you can check with your calculator. And the very last part of the chapter in F is absolute value functions or modulus functions. So basically, it's a distance. So when we're trying to figure out distance, if we take the modulus of a number, if it's positive, it stays positive. If it's negative, we make it positive. So it is just an absolute, which means it is well, yeah, you can talk about it in terms of distance. Distance is always positive. So the algebraic definition, sometimes we want to go from the modulus back to what we had before. So in that situation, if x is greater than or equal to 0, it's x. And if x is less than 0, we say it's negative x. So that's represented by the graph underneath, where if it's positive when x is greater than or equal to 0, you've got y equals x, the graph. And below 0, it's y equals minus x, which is why you've got the V-shaped graph. An equivalent definition of the modulus of x is the square root of x squared, because obviously if you've got a negative number, if you square it, it'll become positive. Then taking the square root of that positive number, you'll get a positive, and you'll get, if x was negative to start with, it'd be converted to positive. If it was positive, you'd get the same thing after doing the square root of x squared. So basically what that does is it just removes a negative sign, that square root of x squared. So it satisfies the definition of absolute value. So the first part of this chapter is just plugging in numbers and getting an answer. So for 1a, the modulus of negative 2, because a is negative 2, is just positive 2. So those ones are very simple and straightforward. Pretty basic. So yeah, it's just a lot of practice drills basically for these, which is good to do, because if you can nail this, it's going to build your confidence. Graphs involving the absolute value function. So here we've got a couple of different graphs. So you've got f of x as a quadratic, 3x times by x minus 2. And we're looking at the y equals f of the modulus of x compared to y equals the modulus of f of x. So they're very different. So in the first one in a, y equals the modulus of x. So basically, for any negative x value that we have, we're going to get the y value that we've actually got on the right hand side of the graph. So on the right hand side of the y-axis actually. So it's going to be a mirror in the y-axis, that graph. And on the right hand side, modulus of the whole of f of x. So you're looking, instead of the modulus of the x term, you're looking at the modulus of the y term. So anything that's negative y in the original quadratic will be made positive, and so then that's why you get that hump above the x-axis. So the bit under the y-axis is reflected in the x-axis, and then the rest of the graph stays the same because it was positive to start with. So the modulus of a positive isn't going to affect it, so that still stays the same. So that's F2. So this will follow a similar concept here. So you just have to think about what you're doing and apply it. And then an extension here. So that's where we've got a modulus and we're looking for the solutions. So the modulus of 2x plus 3 in the example. So when you remove the modulus, you make the right hand side plus or minus, and then you'll get two solutions. And in B, if you have the modulus equals a negative, that can't exist because obviously a modulus of anything is always going to be positive. So that's got no solutions in B. So it's just a matter of then going through these. Yeah, so in example 10, if you've got two moduluses and you remove both of them, it's going to be plus or minus just one of them because that's covering all cases that you could possibly have. So that's what that shows, and you'll still get your two solutions. And then it's just, that's the end of the chapter. So I hope that that gave you a good summary and was helpful. And yeah, see you next time.